Okay, so I think that, are you ready, Shachar?
All good,
Okay.
yeah.
So yeah, this is another beautiful thing that for me that these methods are so useful in geometry, and it's actually many of the arguments are very geometric, and at the same time they are sort of suitable for attacking classical combinatorial problems like the sunflower lemma, this big breakthrough, and all of these papers, Shai's paper and Shakar's paper, they got best paper awards on Fox and Stock, and I believe I understand why. So thank you very much for accepting our invitation.
Yeah, actually, thank you for the organizers for inviting me. This is and for organizing this workshop. I mean, I couldn't join the early talks because it was too early for me. I'm in California, but the talks I attended were really nice, and really appreciate you organizing it. Yeah, so really what I want to talk about is to some extent a follow-up to what Shai was talking about on the conceptual side. I mean, so what Shai described is saying, well, if whether it's in geometry and you want to solve point location, or whether it's in machine learning and you want to sort of label points. I mean, if the points are nice, the data is nice, and then we can solve it near optimally. But what if it's not nice? What if it's somehow adversarial? So this work I want to tell you about is really about making zero assumptions about the data, about the input, and asking what can we do then. And this is also, I want to say, this is a joint work with 3 people at UC San Diego. So Max Hopkins and Gaurav Mahajan, who are students, and Daniel Kane, who's faculty. Okay, so we begin. So really the starting point is this very, like you said, a very classical questioning in sort of, combinatorial geometry of point location. So you have a partition of, d-dimension Euclidean space given by hyperplanes. And it's also called the hyperplane arrangement. And you have a point that you don't know. So you know this partition, everything is known to you. The only thing you don't know is this red point. And your goal is to find the cell in the partition where this point is. Like in this example, that's going to be the cell. So it's sort of, this triangle. And the model, the computational model here is, like I was describing, this linear decision tree model. It's called LDT, or it's abbreviated LDT, where we're assuming we don't have direct access to the input. I can't just ask, well, what is the input? What instead you can do is query the location of the input relatively to some arbitrary hyperplane that you choose. And the question is, well, how many queries do you need till you can figure out the cell? So let me show you an example. I think maybe an example would make it easier. So if this is my hyperplane arrangement, and this is my red point that I don't know, maybe first I choose to ask about this red line, and I get the answer, well, it's below it. So now I know that my input is somewhere in this shaded area. And then my next question is going to be about maybe this line. And then I realize, well, it's actually in this shaded area, the smaller one. And then maybe, I decided to ask about this bottom line, and then I get this sort of triangle, which is not quite the right answer. So I ask about, I still don't know. Respect to the last line, so I ask again, now it's in this smaller triangle, and I'm done, right? Now I know the location of the point, which basically, notice that this cell means that I know the location of my input point relatively to all of these hyperplanes, all the lines in this picture, right? I know for each one, whether it's on the left or the right or on top of it. Now for this talk, I mean, the case of being on top of it doesn't really make a big difference. So it would be perfectly fine to assume that everything is either on the left or the right. So that won't change anything dramatically. Okay, so we're happy here. And actually, I was saying this is really this sort of, the reason it's called the linear decision tree is because this computational model, the way it accesses this unknown input point X is via linear queries. So every time you ask a linear query, you get an answer, whether the result is negative, 0, or positive, and then you adaptively continue. And your goal is to minimize the number of queries you make, which is the depth of this tree, until you figure out the answer. And okay, just to get some formal definitions, so that we're all on the same page, I'm going to denote by n always the number of hyperplanes. I'll assume always that the hyperplanes are through the origin, the homogeneous, just to simplify notation. And so they're given a hyperplane is always going to be given by its normal vector. So H1, for example, is going to be the normal vector to the first hyperplane and so on. So I have n hyperplanes in RD, I have an input point. And what is a cell? Well, the cell is basically determined by knowing for each hyperplane whether the point is on the left of it, or the right of it, or on top of it. So if the inner product is negative, 0, or positive, so -1, 0, 1 to the n. So it's by this long vector with 3 to the n possible answers. That's like, a way for us to determine the cell. And what is a query? So a query is basically I can choose whatever hyperplane I want. So remember, H is given by a normal, right? So every normal that I want, I choose a query X with respect to it, and I get the answer. And my goal is, again, to minimize the number of queries I need until I can find the cell of this point. So this is a very classical, combinatorial geometry question. And of course, if you know how to solve that efficiently, then you might want to do it also algorithmically efficiently. But in this talk, I'll just be focusing on the combinatorial aspect. And there are very simple bounds here that you can get. Like, for example, if you query all the n hyperplanes, then definitely you can do it, figure out all the signs, but it turns out you can do better. But there's also a lower bound, and the lower bound is actually d log n. Remember, d is always going to be the dimension where we're operating, n is always going to be the number of hyperplanes. So you need d log n. Why? Well, the reason is simple. If you take n generic hyperplanes in RD, so they partition RD into some number of cells, and if you calculate the number of cells, you get it something like n to the d. And every query you ask only returns once of some constant number of answers, like in our case, -1, 0, 1. So you need to figure out an answer, 1 out of n to the power d possible answers, and every question you ask only returns one constant number of answers. So this gives you a lower bound the number of questions you have to ask. So this is this d log n. And notice this lower bound doesn't assume anything about the fact that my questions are geometric. They're asking about hyperplanes. This will be true for any type of query that gets only a small number of possible answers. So the main question we are trying to understand, it's been around for the last probably at least 40 or 50 years, is can we match this very simple information theoretic lower bound using geometric queries? So I'll tell you soon what's known about it. Before that, I just want to tell you about this sort of dual viewpoint that Shai was talking about of active learning. It's going to be the same mathematical problem, but just using duality, but it'll be more convenient for us to use. So let me sort of skip all the introduction because Shai was talking about it. Let me go to the math. So here's the math. So you have, now you don't have a hyperplane in RD, you have points. And what you don't know is a hyperplane. And your goal, maybe I have a picture here, that'd be easier. So what I have here is these blue points. That's what corresponds to the hyperplanes before. Now I have these points in RD. This is what you know. What you don't know is this red hyperplane. And your goal is to label all these points. So your goal is to figure out for each point whether it's on the left or the right, or maybe on top of the hyperplane. Right? Like in this example, our goal will be to say, well, we want to find that all these points on the right are labeled plus and all the points on the left are labeled minus. So that's the goal. Okay, but what queries can I make? Well, of course, if I knew the hyperplane, I could just do it myself because remember, all these data points are given for me. So the only access I have to this hyperplane is via making queries. And what are the queries? Well, I can choose whatever point I want, one of my points or maybe another point, and query on which side it lies. Like for example, here, I could decide to choose this point, this purple point, and query it, and I get the answer, it's on the right. So I could choose whichever point I want and query it, as long as at the end, I know how to label all these endpoints. So again, that's always going to be the setup. I know the points. The only thing I don't know is this hyperplane, this red line. And the only access I have to this red line is via arbitrary queries of points. And like, the example Shai was saying before, these two problems are the same, right? Just of two different ways of viewing the same mathematical problem. So in the point location problem, we have known hyperplanes H in RD set. We have an unknown point X in RD. Our goal is to decide the sign of the inner product of X and every hyperplane in the set H. And we can do it by choosing an arbitrary H in RD, well, it should be RD, not Rn, and taking the inner product of X and H. And the active learning problem is exactly the same mathematical problem, except that we just dualize points and hyperplanes. So of course, we can choose whichever one we want. It's the same problem. I'm going to choose this sort of active learning one, the one where this point that I want to label, because of two reasons. First of all, for me personally, it's more intuitive to think about it. And also, as we'll see later, it is because it's coming from this machine learning perspective, it's easier to apply machine learning techniques in this problem, and that we use for us. So but I think this is just for convenience. You can do everything that you do here in this original point location, hyperplane arrangement setup, because it's the same problem. It's just about which one is more intuitive to you. Okay, so now let me tell you about what are the results that are known. So here's a summary of everything that's known before the work, this recent work I'm going to tell you about. So again, the setup is always going to be the same. We have endpoints now in RD, or in the point location setup, and hyperplanes in RD. And the lower bound, like I said before, is this very simple information theoretic lower bound of d log n. And then the upper bounds that we have, and most of them come from this computational geometry or discrete geometry viewpoint of this point location problem, is that, well, first of all, surprisingly, already by this work of Meiser from early 90s, is that there is a way to do it much better than n for general problems. So the first point to do it was Hufdermeyer for a specific problem, but then Meiser generalized it for general point location problems. And the bound was d to the power 5 log n, which is already amazing. The fact that you get a polynomial depends on the dimension, and only a logarithmic depends on the number of points. So now the whole question remains: is it d to the 5 log n or d log n? Like, what should be the right dependence on the dimension? As I'll show you, this is actually a tricky question, and this is where all the fun is happening. You're trying to get the right dependence on the dimension. And there was a sequence of work of a Cardinal, Iacono, and Ooms improved the 5 to a 3, and then Ezra and Sharir improved this to something close to quadratic. And then the work Shai was telling you about got this to be near linear, assuming that the points are nice. So we need some assumption on the points or the hyperplane. They can be arbitrary. But the benefit was this only used simple queries. So we didn't have to query arbitrary points or arbitrary hyperplanes. We cannot choose to do comparisons. So now what I want, but also we know from that work that just using these simple queries is not sufficient once you move to adversarial configurations. And it's not so hard to build these adversarial configurations. So the main motivation behind this work is asking, well, can we leverage any of the understanding we had there to basically solve this problem better? So to some extent, the answer is going to be yes, we want to get better bounds, but to some extent, the answer is going to be no, because we're not really going to be using this inference framework, inference dimension framework. We are going to be influenced by it, but at the end of the day, the work I'll tell you about doesn't actually use the inference dimension, implicitly or even explicitly. So here is a new bound I want to tell you about, is that an arbitrary point location problem with endpoints in RD. So the bound you can get looks like that. So the first part, this d log square d log n, is what we were hoping to get. And this is optimal up to this log square d bound. And for some reason that you'll see later on, we also have this second additive part that doesn't depend on n, just on d. And it's to some extent, it's near linear because the power of d is close to 1. And to some extent, it's very not close to linear because of this 2 to the root log d factor. So this looks like a very weird thing. Like, why do we get this factor? And you'll see later on why this comes. A lot of what I'll tell you about is going to have this first part. This is really close to d log n up to this polylog d factors. And only at the very end, we'll have to pay this extra price. And I think there is a lot of potential to improvement. I think what we do there is really far from optimal. So, but you get to see why closer to the end of the talk. So maybe before I'll start telling you about, well, how do we do it? Maybe now is a good time to see if there's any questions about the results. Okay, so let's start. So how do we prove it? So again, here's the setup. Let me just recall the setup so that we're all on the same page. So we have this known set of endpoints in RD. We have an unknown hyperplane in RD given by its normal vector. It's homogeneous. My goal is to learn the labels of all the points in X, meaning on which side of H do they lie. And my oracle, I have an oracle where I can query the label of any point in RD. So I'm going to make one assumption and two definitions. It's going to be convenient for us. First of all, I can assume that all the points and hyperplanes are just unit vectors because renormalizing them doesn't affect anything in the labels. So nothing changes, just for convenience for analysis. So the label of X and H, I'm going to denote by LXH, is just a sign of this inner product. So this is what my query is giving me. But for the analysis, we also need something called the margin, which is just the absolute value of this inner product. Okay, so the L is always going to denote labels. Think of -1 or +1. You can even ignore the case where it's 0. Let's say this never happens. And margin will be the absolute value of the inner product. So we'll need both in the analysis. And the general paradigm is going to be the follows. Somehow we would like to make something like D queries and learn the labels of half the points. So you see the number of queries we make is independent of the number of points, just D, but we don't get to learn the labels of all the points, just some constant fraction of the points. And then we just remove this and repeat. So this will give us this D log n that we're trying to get. And throughout the talk, I'm going to ignore polylog D factors. When I write sort of approximate, I would always mean up to some polylog D factors. So just for convenience, I'm going to, for the most part, ignore polylog D factors, but not log n, just polylog D. And we will do this in steps. So we'll start with a very simple scenario and we'll keep complicating our lives and we'll see what breaks down and what do we need to do to fix it. So the first step is just, what if my points were random or like generic, nothing super special about them? And we'll see this, in this case, it's actually not that hard to label many points. So let's say all my endpoints were like random on a sphere or something. And then the inside is a random point would typically have high margin. It will not be like super close to the hyperplane, right? So if I fix a unit, vector H, which is a normal to my hyperplane, and I sample a random point, unit vector X in RD, then you can show that with good probability their margin, their inner product is going to be not too close to 0, something like 1/√D. So what does this mean? And we'll see that with high probability, again, this is just for intuition at this point. We don't really have random points, but this is for intuition. If my points were random, well, half the points are going to have high margin. So we'll see how to learn the labels using something like D queries. So, or more generally, we won't really be using the fact that they're random, just that they have high margin. So let me show you something that sort of, if I have, let's say, half the points with margin epsilon, then you can learn the labels using something like D log 1/epsilon queries. Now, Shai showed you how to do it just using comparison queries. And that was sort of required some work. Let me show you that by using general queries, not comparison queries, this is actually very, very easy. But of course, then we need to use more general queries. But this is just going to be our starting point. So why? So here's a simple idea. Let's say my hyperplane is H1 to HD, and my point that I want to label is X1 up to XD. Assume I could just approximate each HI up to some small enough error, like epsilon/D. Well, in that case, I'll show you how to do it in the next slide. It's very easy. In this case, I can just estimate the inner product up to error plus minus epsilon. So in particular, if my point X if the value I get is much more than epsilon, let's say more than 2 epsilon, I know it has to be either positive or negative. So by approximating this normal to the hyperplane, I could very, very easily just label all the points with large margin. So how can I do that? So this is just a very simple, argument. So what are the coordinates? Just the inner product with the standard basis. So now, let me not go through the details, just it's very simple, sort of a bunch of labels and comparisons. You can just approximate all of the things up to some small enough error and approximate everything. There's nothing super interesting going on here. All I'm saying is that, maybe this picture is the best way to think about it. Let's say we have this green line that I don't know, but I can approximate it to be roughly, I know roughly where it is. Then if a point is far from it, I know if it's on the left or the right. So all the points I don't know are the ones that are very close to the green line, so that, if I make some error in approximating it, then I'm not quite sure if I'm on the left or the right. So all that you need to get from this first part is saying, well, it's very easy to learn the labels of all the points of large margin. So all of the technical challenge comes from learning the points of small margin. And also, let me also add that here we use general queries. If you want to learn this point with large margin using sort of simple queries, it becomes more complicated, but we don't care about that. We're happy to allow arbitrary queries here because we'll have to do it anyways later on. Okay. Any question about this part? This is supposed to be a very simple part. You just approximate the green line and you find all the labels of points not too close to it. Any questions on that?
Can you do this part only using comparison queries, or?
You can only use, like using our algorithm. You can just use our algorithm in comparison. You could do that, but then the analysis is just more complicated, and it won't help us because the later parts are not going to be using comparison queries anyways.
Okay, thanks.
Yeah. I have a question, Shachar.
Yes.
Just the picture for me is somewhat misleading because in my mind the error is sort of not this stripe. This is correct?
Yeah, it's not really a stripe because it's supposed to be like all the points that are sort of far from a hyperplane when they're on the sphere, right? So I couldn't draw a point of the sphere here in the plane because they wouldn't have enough. So imagine points on like a circle and all the points not too close to the green line. Yeah,
so I just wanted to make sure that I understand. Okay.
Yes. This is just for illustration. This is not supposed to be, true to life. All the points think about it this way. All the points where the inner product is too small, I don't know what to do if I just approximate the green line. But if the inner product is large enough, then I know the answer.
Thank you.
Okay, Amir? Yes? Okay, good. But again, this part has nothing interesting going on here. I mean, stuff is going to become more interesting as we try to basically learn these small margin points. That's where all the action is going to happen. This is where a lot of the previous things sort of had some sort of inefficiencies. So how do we deal with these low margin points? That's the question. So the second step is, again, something that already existed in previous works, was this idea of vector scaling. That you can sort of rescale points so that at least some of them have high margin. So let me tell you, in the next few minutes about vector scaling. So again, the idea, so let's assume that all the points have sort of tiny margin, they're like really close to this green line. So we can't hope that just by approximating this green line, we can learn the labels. So the idea would be, well, since we really only care about the labels, not the margin, maybe you can somehow rescale these points. So somehow maintain the label, but sort of change the margin so that now some of the points are going to have large margin. So this is this idea of vector scaling. So this slide is going to be slightly technical, so let's go through it together. So let A be some invertible D by D matrix. So for a vector x in Rd, I'm going to denote the following action of A on X, which is you multiply A by X and then you renormalize so that you get a unit vector. So I'm assuming here throughout that all the vectors you are going to see are unit vectors. So when I apply a matrix on a vector, I'm always going to renormalize it to be a unit vector. Okay, so it's not a linear operation anymore. And let A star be the adjoint operator, so that if I look on AX, A star H, this is just a standard matrix product of A and A star with X and H, I get the same as the inner product of X and H. So A star is the adjoint operator. So here's the idea. Somehow smartly choose A. We'll get to see how to do it soon. But then I want to replace my set of points X and my hyperplane H with a new set of points and a new hyperplane. So what is going to be the new set of points? Is going to be apply A on X. And what's going to be the new hyperplane? Apply A star on H. Remember, apply always means multiply and renormalize to be unit vector. So there are two questions. First of all, three questions. First of all, why can we do it? Why is it useful? And what can we do with it? But let's first see why this doesn't really hurt our problem. The whole point, this maintains labels, but not margin. Right? If I compute the inner product of the matrix A applied to X and the matrix A star applied to H, what do I get? I get exactly the same as the inner product of X and H, but now divided by some constants. It could be positive, negative, it could be, large, small, I have no control over them at this point. Some positive value. So the hope is that somehow by choosing A in a smart way, we can get at many of the things I divide by something tiny, so the new value I get is big. So notice I maintain the label. So the sign of the two sides here stays the same because I just divide by a positive constant, but the value could arbitrarily change. So again, the hope will be that by choosing A in some smart way, we maintain the labels, but change the margin so that many points are going to have large margin. So how can we do that? So here's the theorem that we prove. That is basically an extension of similar theorem that appeared in the literature before. Well, I'm going to say, well, a set X of points in RD is, if it's not degenerate, I'll define degenerate in a minute, then there exists this A such that applying A on X is going to move it to be in something I'm going to think about, but isotropic position. It's going to be approximate, but let's ignore this approximate here. Now, the only question is, what do I mean by not degenerate? And this is where things in the literature sort of, evolved. So what we prove is, in fact, the most general condition, meaning we assume that if X is degenerate, if there exists a k-dimensional subspace containing too many points in X. And you can show that if this happens, then there is no A that's going to move A of X to be even in an approximate isotropic position. So this is really an if and only if. So we have the full classification here, but for our purposes, it doesn't really matter these details. And an isotropic position, I mean, assume many of you know it, but just repeat the definition here. So a set of unit vectors is in isotropic position if basically their projection on any dimension, on any direction, is the same, or their covariance matrix is a multiple of the identity. Or a third way of saying the same thing is that for any unit vector V in RD, if I look on the average squared in a product with this vector, I'm also going to get the same thing. But again, you should think about isotropic position as basically being spread around uniformly in all directions, at least with respect to first and second moments. Okay, so, and the way we prove it basically builds on previous works that did something similar, but for weaker conditions of being not degenerate. And we are able to actually get sort of a full if and only if condition. So, but again, this degenerate condition turns out to be very easy to handle by some other techniques. Let's ignore that. So again, let's go to what we're trying to do. We're trying to replace X and H with this sort of rescaled version of X and H. And here's just a theorem, and here just repeating what is isotropic position. And why is this useful? Well, let's set V to be, it could be any unit vector. Let's just set it to be this applying A star on H and renormalizing. So it's some unit vector. So this would guarantee that at least some fraction of the points are going to have some reasonable margin, like 1 over root D. So we get something. So we can't get that half the points have large margin, but we can get that some fraction, like 1 over D fraction of the points are going to have somewhat large margin. Now it can't be the case anymore that all the points are super close to the hyperplane. So at least we got array with these guys. So we're back in business. So maybe the last thing I just want to briefly say, why can we actually make this? Because we don't really have access to H. We only have access to X. We don't know H. So the whole point is that we can actually simulate queries. So if I want to simulate a label query with respect to this A star H, I can just do it by a different label query with respect to the original H. So that's like a minor point. I mean, the whole point is we can actually, even though we do this transformation in our minds, we can actually simulate labeled queries with respect to this new H by label queries with respect to the original H. So that's just so that what we're doing is actually useful for our purposes. So where do we stand now? So we apply this vector scaling and we get the points to be in this approximate isotropic position. And really what this guarantees, by just some simple Markov arguments, is something like 1 over the fraction of the points have some reasonable margin. And so that by using these techniques from before, just to approximate the hyperplane, we can just learn all the high margin points. But now we have a problem. Remember, what we did before was we invested something like D queries to approximate the hyperplane. And if we really half the points have large margin, then it's good. We invested D queries, we labeled half the points, and we just continue. But now the problem is that, well, it might be that not half the points are going to have large margin, but only a much smaller fraction, like 1 over D fraction of the points. And sort of in general, you can show that there are situations where this happens. So if you just do that, you're going to get D squared log n queries, which is maybe another way of getting the same result of Ezra and Sherrier, but using different techniques. And if you just want to use this of, let's say, a high-level approach of doing, vector rescaling and learning the high margin points, then that's the best you could do. So you can show that you can't really improve this vector scaling. So really, if you want to make progress, we need to sort of dig deeper into the structure of the points. And basically, at this point, the new techniques that we introduce begin. So up until this point, everything that we do is either already known or small variations on known techniques. So this point, going beyond or below D square, this is where we need to introduce all these new techniques. So at this point is maybe, if you tuned out, maybe the good point to start listening again. But maybe before doing that, let me ask you if there are any questions about everything up to this point.
Shachar, is it easy to see how can we get this matrix A?
No, it requires work. It's not something simple. There are different techniques, and none of them is sort of elementary. They require work.
Okay.
But this follows from. But basically, you can do it using. But there have been several previous techniques in the literature to do that, and we just adapt them to get it to work with this exact characterization. Again, that's like a minor point. That's not the major thing. The new thing that we're doing here.
You still didn't tell us what to do if there is a small subspace that captures many of the points.
Exactly, right? Exactly. So now this is what we're going to do. So this is where things are going to become interesting. So what I want us to do now is understand the refined structure of the point sets. Like Shai was asking, what if many points are on a subspace? Oh, let's see if they're exactly in a subspace. No, then it's easy. Just do them and you recurse on the rest. Then you can do the calculation. That's very simple. If you have a k over d fraction of the points on a k-dimensional subspace, you just solve them independently and then do the rest. That's easy. So the hard part is what is approximately in a subspace. That's what things are going to break down in these analytical measures like vector scaling, but you cannot just do simple induction. And this is where we need to look on this refined structure of these point sets. So okay, so now here's going to be the new thing. So let's assume already we are in this isotropic position to simplify our lives. And now I'm going to do the following exercise in my mind. I'm going to take my endpoints and I'm going to sort them by margin. Now, I don't know the margin, but I can still sort of in my mind play this game.
Shachar,
yes.
I'm sorry, about the previous question,
yes.
About finding A, not proving that it exists, sorry. If you compute the covariance matrix of X, then it tells you what A is, or roughly?
No. Well, no, I don't think you can do that. Just with the covariance matrix. You do it within all the points because this rescaling is a nonlinear operation. So these techniques are iterative, and no, I don't think you can just do it using the covariance. As far as I know.
Because eventually the covariance matrix changes by multiplication in A.
But you multiply by A, then you rescale each vector to be a unit vector again. So this is like a vector by vector operation.
Yes.
So it's not just given by the original covariance matrix. No, that's not so simple. But let me sort of skip from this issue. Let me already assume that you're in this isotropic position, so we don't have to worry about it. Because this is really the main thing I want to tell you about. This is the new ingredient in this work. So let's say I take all my points and I sort them by the margin. What do I know? I know that some fraction of the points, the first n over d of them, are going to have some large margin. But I know nothing about the rest. And up until now, we just use these first n over d points to say something. And now I want to ask, well, what can I say about the rest of the points? And the point is there could be two cases. One case is all the margins are relatively large. It's actually a good case for us, because if many or all the margins are relatively large, we can apply these previous techniques. And the other thing that could happen is that there's a sharp drop. Up until some point, many margins are big, but then from not too far after that, they drop. What does this mean? It means that many points lie very, very close to the hyperplane. So really the points I have that are far, to some extent, have to live in a small dimensional subspace. So we can hope to do dimensional reduction. So that's going to be the main thing I want to tell you about. And at this point, it might be not clear why we can do it, but you'll see why. Hopefully we have enough time. So here's the first lemma. It says, for any set of points, you can always find a k between 1 and d, such that the following thing happens. If you go all the way up to k times n over d, then all of these are going to have high margin. If you go slightly above it, from 2k n over d, just index times 2, you're going to have low margin. So like maybe the first L points are going to have high margin, and from point 2L and above, you're going to have very, very small margin. And really what we're going to see is that there are these two regimes. If k is very big, we have many points with high margin. If k is small, there is this sharp drop. that we're going to utilize. So here are the technical details. Let me sort of skip that, but this is a proof. The proof is very easy. You can look through it later on if you want. I'll show you the slides. There's nothing, this is like an elementary proof, but let me sort of show you why it's useful. So we have this sort of lemma. Here's going to be the main thing that we could do. We can take this lemma plus the assumption that we are in this isotropic position and show that there is actually a large subspace where every point in this subspace must have low margin. So here's a maybe slightly more formal definition of this lemma. So given this parameter k in the first lemma above, we can find a subspace of dimension something like k, that all the points in the orthogonal complement of this subspace are going to have low margin. What does this tell us? It tells us actually if we take all our points, if you could somehow find this subspace V, and we can take all of our points and project them to V, then we can solve my problem of high margin points, not in D dimensions, but in K dimensions. Now this parameter K is not some arbitrary parameter, it depends on my point sets. For different point sets, you're gonna get different parameter K. But for what we prove is for every set of points, there is this parameter K that would allow you to do dimension reduction. So again, I'm gonna sort of have the proof here. I'm going to skip the proof, but it's basically using something like looking at this covariance matrix of the low margin points and understanding the eigenvector structure. But I'm going to skip the proof for the sake of time. So this subspace, and now all that we're going to do is observe that the high margin points, if they're high margin to begin with, they have to stay high margin if they project on V, because everything in V perp has very low margin. And so we can just solve the problem for these high margin points, not in D dimensions, but in K dimensions. So what we prove is really the following thing. If you put everything together, you have this subspace in RD of dimension K, where some K over D fraction of points have large projection on V. And this is the same K. Here's where we pay, here's where we gain. It's the same K. The fraction of points of large margin is exactly the same, this K is exactly the same as the dimension of the subspace on which we're going to project them on. And if we knew V, if you could somehow know V, we just take all the points that we know, project them to V, and ask which points are still going to have large margin. Remember, somehow we are guaranteed that all the points in V perp are going to have low margin. So if a point in V has large margin, it also had large margin to begin with, we just work everything inside V. So we can solve this problem not in dimension D, but in dimension K, is high margin. So we only query about K points instead of D points. So we get this coupling between the number of queries we make and the fraction of points on which we learn the labels. And that's really the new thing that we do here. Saying there is a way of solving this problem by doing a dimension reduction if you could somehow identify this subspace V. So we can prove it exists. Question is, how can we identify it? I'll get to that in a minute. But just sort of to summarize this part, is the following thing. By doing this type of more refined analysis on this structure of the points, we show that by querying K points, you can learn the labels of K over D fraction of points. So you can keep doing that until you basically get something like D queries, at which point we label half the points, and then you can just recurse on the rest. So this was all good, nice and good if you could somehow efficiently find this structure K and V using few queries that I haven't shown you how to do yet. So all I did so far is prove existence. But what we need to do is somehow find it effectively, because it depends on the hyperplane that I don't know. So that's going to be our almost last point. Any question at this point? So again, what I really want to take from this is that at this point, we broke away from doing that works for every set of points. We really identify some parameters that are specific to our given set of points. Okay. So maybe the last thing I want to tell you about, or almost the last thing, is, well, how do I identify them? And okay, let me I don't think, how much time do I have left? Janos or Shai?
2 minutes.
2 minutes. Well, then really I have no time. So let me just tell you one thing before I finish. So the way to do it is to define a new type of query that we call the Approximate Max. And Approximate Max is a following query. It's a new type of query. It says, well, given a list of points, find a point inside it that doesn't have the maximal margin, but is approximately maximal margin. So if I had 15 more minutes, I could show you why we can use it to find this K and V efficiently. Also, how we can use a few standard queries, randomized queries, to approximately simulate it. And again, for the sake, I don't have the time, so I can't really show you, but I can, if people are interested, I can show the slides and just, I guess, didn't plan enough for time. So there's a way to do it. And basically put this all together. What you get is something that would, there's some error in the algorithm, you get some weak learner in the machine learning, I would say, terminology. You can use the boosting algorithm to get a strong learner. And then there's this part where we pay this weird parameter that I want to tell you about, maybe in the remaining 2 minutes, which is, turns out the main thing we need to do to get better bounds is the following question. That seems to be much easier. So imagine you didn't have to label all the points. I gave you the labels. I gave the points and I gave you the labels. And you just need to make sure that I'm not cheating. So you just need to verify that the labels you got are correct. How hard can that be? So we don't know. What we can show is that you can reduce this question to basically point location in low dimension using the internal structure of our algorithm in a very complicated way that I don't like, but it works. And we pay this weird additional factor. But really, I think to me, that's the most, I would say, pressing remaining open problem here, which is, what if I gave you all these labels of all these points? How hard it is just to verify it is correct? So maybe just, again, I'm going to skip everything here. Just to summarize, our algorithm has this, it works for arbitrary list of points, arbitrary point location. It has 2 parts, the number of queries. The first part is this near optimal bound. The second part that I don't like is just verifying the solution, because it turns out the first part has a small probability of error. And this verification is where we pay this weird, quantity. So I'm going to stop here, and then if people have questions, then I can answer them. Thanks. Yeah, sorry for taking more time.
Thank you very much for the nice talk. There is one question I see. Maybe there are more. Wait a second. Can you talk about the algorithm, the slide before the summary?
This one?
Yeah.
So it has 3 main components. The first component, I'm going to call a weak learner. The weak learner is going to be this algorithm. So just the definition, what it does. Here's what it does. This is a weak learner. It's a randomized algorithm. It's going to be a randomized linear decision tree that does the following thing. For some of the points, it gives labels. For some, it doesn't. With 99%, it doesn't make mistakes and labels 99% of the points correctly. And the others, it doesn't label. With 1%, it gives you an arbitrary answer that you have no control over. Okay? And it also makes something like D or DPOI log D, regular queries. The way we get this algorithm is getting an algorithm without error that uses this new type of query, Approximate Max. And then the error comes by simulating its Approximate Max queries using standard queries. So I haven't had the time to talk about that. So that's like one part. This is maybe the main ingredient. And then to get from this almost correct, almost all the points algorithm to always correct, always all the points algorithm, you need 2 steps. First step is pretty standard, doing boosting. I mean, there are some tweaks here because you can't really do standard boosting algorithms here because you can't really know. In standard boosting, you know which points are correct or not. Here, we don't know, but you can get around that. Then you get an algorithm that still has a small probability of error, but now it labels all the points correctly, all the points. And with 1%, it gives some arbitrary labeling, 99% the correct labeling. That's relatively standard. And then a lot of work goes into how do we actually verify this solution. And this here, the way we have is very ad hoc, and I don't like it. There should be a better way. Like, I think there should be a black box way. Let's say I gave you an algorithm that labels all the points using optimal number of queries and has like 1% chance of error, and otherwise labels all the points correctly. Can you use this in a black box way to verify labeling efficiently without any errors? So we don't know how to do it in a black box way. We only know how to do it in a way that's very specific to the way we run our algorithm. I think that's a very intriguing open question. Another thing is that we don't really have a deterministic randomized. We don't have a deterministic decision tree. We only have a randomized linear decision tree. Yes. I don't know if this answers the question or not. But really the algorithm has 3 parts. This weak learner part, this boosting part, and this verification part.
Okay, thank you very much. Well, if there's a very, very short question, maybe someone wants to ask. If not, then thanks, Shachar, for the nice lecture.